In this video, we look at capacitors. The capacitors can store energy and deliver the energy later on. The resistors, which we have considered a lot, they cannot store any energy. So capacitors can store energy, but resistors cannot store energy. This is one of the biggest difference between capacitors and the resistors. How do we build capacitors? We use two metal plates here. This is a metal plate. There's one metal plate on this side, and there is another metal plate on this side. And in the middle, that's insulator, also called dielectric material. If this capacitor is connected into a source, for example, a voltage source, there will be electric charge on both this metal plates because metal plates are conductors. And there will be magnetic field formed between these two metal plates. The insulator prevents the loss of the electric charge. Therefore, the capacitor can store energy. The thing about this, the charge that's stored in the capacitor is proportional to the voltage across the capacitor. Therefore, Qt equals to C multiplied by V of T. So this constant C, that is capacitance. The unit of capacitance is farads. F is 1 coulomb divided by 1 volt. What is capacitance? C equals Q, which is the unit of coulomb, divided by the voltage, which the unit of volt. 1 F is equals to 1 coulomb divided by 1 volt. The value of the capacitance is determined by the material of the capacitor. This is a 3D view of a capacitor. This is the area of the metal plate, and this is the distance. This is the front view. This is the front view. It's the distance between the metal plate. The capacitance is equals to epsilon multiplied by A and divided by D. Epsilon is a constant, which is the permittivity of the insulator between the metal plates. Next, let's look at the current voltage relationship for the capacitors. We know that current is the derivative of the Q, the charge, with time. Basically, that's the change of the charge with time that's formed the current. We know that Q for the capacitor is proportional to the voltage. So Qt equals to CVT. So plug it in, we take derivative. And C is a constant, we take it out. So I of t equals to C derivative of V of t. And this is the current voltage relationship for the capacitor. Let's look at this circuit here. This is a capacitor, the current I of C, and the voltage here. This notion, observe the passive sign convention. Then, in this case, the current voltage relationship for the capacitor is IC equals C dVc dt. IC equals to C derivative of V with respect to time. Then what is the voltage along the capacitor? Then we do integral. We take this, we take C out to the side, so and then we take the integral from minus infinity to time t, and this is a time t, this is a variable t, and IC do the integral with respect to time. This notation here, because this is a time t here, this is t, a little misuse the notation. So normally, mathematically, it should be written like this. That equals 1 over c minus infinity to t I of c u d of u. U is the dummy variable for the integral. But if without confusion, this notation is okay. If we have initial state t naught, so Vc of t equals to 1 over c, do integral from minus infinity to t naught and t naught to t. This is equals to this. Therefore, the voltage on the capacitor is equals to the initial voltage plus this integral. Let's look at the power on the capacitor. Because of this notion, observe the passive sign convention already. So the power on the capacitor P of C, C means capacitor, is a function of time. So there's a function of t that equals to V of t multiplied by I of t. The subscript C, which means capacitor. I of t equals C dV dt. Plug in IC here by this quantity, so we obtain this relationship. So this is the power on the capacitor, which is a function of time. What is energy stored in the capacitor? Energy is integral the power. So we do minus infinity to time t. This is a misuse of the notation, but if there's no confusion, that's okay. We need to pay attention here. This is a function of time. This is a function of time. Plug in the power. So the energy is stored in the capacitor. We do integral from minus infinity to time. We do a little integral here. After some mass organizations, the energy stored in the capacitor equals to half C Vc squared. Some important properties of capacitors in the circuit, which means that the capacitor is connected into a circuit. If DC is applied to the terminal of the capacitor, then there's no current flow through the capacitor. This can be understood by the current and voltage relationship of the capacitor. ICT equals to C derivative of the voltage with respect to time. If Vc of t is constant, which is DC, then derivative of a constant goes to 0. That equals 0. There's no current flows through the capacitor. No current. In this case, the capacitor is treated as open circuit. The other property is the voltage across the capacitor. It cannot change abruptly. This can be understood by the voltage across the capacitor is the integral of the current. We know that integral mathematically smooths the curve out, so there is no abrupt change for the voltage along the capacitor. These are two important properties of capacitors when the capacitors are connected into a circuit. Next, let's look at the capacitors connected into a circuit. In this case, there are multiple capacitors in series connected in a circuit. We want to find out the equivalent resistor for all of these connections here. Again, using KVL and the voltage current relationship of the capacitor, we plug it in. Then the equivalent capacitor follows this relationship. And this is similar to the formula of when the resistors are in parallel. Next, let's look at all the capacitors are in parallel connected using KCL and the current voltage relationship on the capacitor. We plug it in. Then the equivalent capacitor is summation of all those capacitors, C1 plus C2 up to Cn. This formula is similar to the resistors are in series connections. Let's do the summary here. Capacitor in DC, open circuit, we talked about that. And this is the important current voltage relationship or voltage current relationship. If the capacitor are in series, if the capacitors are in series, this is the equivalent capacitor. If the capacitor are in parallel, that's the equivalent capacitor. And this is the value of the capacitance is related with the material, how the capacitor is built. This is the voltage, and this is the power, and this is the energy.